a lot of places so far in chapter 14. We've learned why electron delocalization is stabilizing by considering the kinetic energy operator. The curvature of a function is related to its kinetic energy for a wave function. So this wave function has a higher second derivative, it's more curved, and so it will have a higher kinetic energy. Therefore, if you have a wave function that spreads out more, it will be stabilizing. And indeed, this is one of the things that makes a bond so stable. If you consider, say, if we were to graph the wave function for a 1s orbital, here's the wave function. I'm only graphing the real part, and then here's some distance. It would look something like that. But if we were to bring two 1s orbitals together in hydrogen, we would get a wave function that looks something like this. And notice that the wave function in between the two nuclei, this would be hydrogen A and this would be hydrogen B. Notice that the wave function in between the two nuclei is less curved than it would be in either of the atomic wave functions. So you may have thought, and rightly so, that bonding is because you have two negatively charged electrons holding together two positively charged nuclei. And you've seen in the Hamiltonian there is a term for nuclear attraction to electrons. But another major and important point is that in bonding orbitals, there's less curvature. The electrons slow down. They have lower kinetic energy. And therefore the orbital itself has lower energy. We also learned that if you mix two orbitals together, because of this overlap integral term in the denominator, the bonding orbital is stabilized by a certain amount and the antibonding orbital is stabilized by an even larger amount. And we talked about how that's the origin of closed shell repulsion. Filled orbitals interact in a destabilizing way. And if you were to fill an antibonding orbital, you don't just cancel out the bond, you now make it totally unfavorable to have those two nuclei close to each other. And this is the basis for steric hindrance and other effects. We talked about how if you bring two orbitals together and they're not at the same energy, and there was a ton of math involved in this, that the bigger the gap between the two orbitals, the less the bonding orbital is stabilized and the more the antibonding orbital is destabilized. So this is, you may have heard this concept in terms of orbital overlap, and that's not technically what that term means. But when you combine two orbitals together, if one is lower in energy than the other, it's not going to be as stabilizing as if the two orbitals were mixing together with the same energy. We also showed that if this gap between the two orbitals is large, the bonding orbital is mostly on the atom that had the lower energy orbital, and the antibonding orbital is mostly on the atom that had the higher energy orbital. And we mentioned this in the context of carbon and oxygen, right? Oxygen is lower in energy than carbon. You know that because its electronegativity is lower. And what that means is the bonding orbital, we would call it the pi orbital, is mostly on the oxygen, whereas the antibonding orbital, the pi star, is mostly on the carbon. And this actually has implications for reactivity. We talked about how nucleophiles like to attack carbonyls at the carbonyl carbon. Another interesting thing is that, well, actually, we'll save that for later. But thinking about this pi star, most of the LUMO is on the carbonyl carbon, and that's why most nucleophiles attack there.
I have a question.
Yeah.
What would be an example of the middle?
This case?
Yeah.
This would be like a carbon-carbon pi bond. I can't think of a good. I don't know. Maybe nitrogen.
So just something that's less electronegative.
Yeah, something less electronegative than oxygen. So maybe nitrogen. And I think you can show that imines, for example, are less reactive than carbonyls, and it could be for that reason. All right. Let's see. Oh, that was it. So we've got a little bit of a ways to go. We want to explain the origin of the Pauli principle, which you have heard as what? Have you heard about the Pauli exclusion principle? What does that say?
The way that we've learned it is probably that two electrons in the same orbital have to have opposite spins.
Right. Two electrons in the same orbital have to have opposite spins. Another way of saying that is no two electrons can have the same spin and the same spatial distribution. But it's more complicated than that, and the origin is actually in some math that we want to do. And we also want to explain Hund's rule, which is that if you have a choice and you have unpaired electrons, it's better for them to be parallel spin instead of anti-parallel spin. So that takes a little bit of doing, and it's going to be a little bit painful as far as the math goes, but the payoff's pretty good, and it actually sets us up to do modern computational chemistry. And I'm working on a computational assignment, and I hope to be able to talk with you about it next time or the time after that. So let's continue on with our consideration of bonding, and let's think of a generic molecule. We won't worry about how many nuclei it has, but let's go ahead and say that this molecule has 2 electrons and they have opposite spin. Okay, now we're going to talk about how to represent the wave function of this molecule that has 2 electrons with opposite spin. All right. Let's go ahead and say that we'll use the Greek letter phi and the subscript 1 to indicate that this is a wave function with a particular spatial distribution. And we're going to use the same symbol phi with a bar above it to indicate that these 2 wave functions have the same spatial distribution, but opposite spin. One of the things your text says is that you can take a 1 electron wave function and decompose it into 2 parts. The first part, we'll use the Greek letter theta. I couldn't think of a better one. This describes the spatial distribution of the electrons. So say for a 1s orbital, this would be the sphere. And then the second part of that wave function multiplied to that spatial distribution is a spin part, a spin wave function. Now, you've normally thought of spin as being just a quantum number, an integer, plus 1/2 or minus 1/2. But you can also think of it as part of the wave function. Remember, the wave function has to contain everything there is to know about the electron, so it's only natural that spin would be a part of that. One thing you may notice here, instead of thinking about an orbital as one wave function that can accept 2 electrons as long as they have opposite spin, we're now considering wave functions to just represent 1 electron. Yeah, so it's a good question, and I think the answer is going to be, I don't know. Spin, you may have been taught that spin is sort of related to an electron being a charge and rotating and therefore having a magnetic field. The spin quantum number, I believe, is an angular momentum quantum number. Or a magnetic moment. And so you can think of it as just as an innate property of the electron. It can have 2 options. And somehow that property, you can detect electron spins. There are some molecules, some elements that have unpaired electrons, and you can actually use a magnetic field to detect them. You can, if for example you have a stable radical and you go downstairs to do NMR of it, that unpaired electron is going to mess with your signal. And there's a whole technique called electron paramagnetic resonance that's about detecting unpaired spins. So yes, there's two options, and yes, it has to do with a magnetic field. Beyond that, it doesn't actually have to do with the electron rotating, because of course we're dealing with the electron as more of a wave than a particle, and so rotation doesn't make a lot of sense.
Right.
Yep, I'm sorry I don't have a
No, that's
better answer for you than that. Okay, so phi 1 and then phi 1 with the bar over it have the same spatial distribution but opposite spins. Okay, that's important. It's going to be important as we continue on with the discussion today. All right, so let's talk now, setting up this molecule. I'm trying to see if we need any other things. I'm going to use notation like this. This means electron number 1 in orbital phi 1. We're going to give electrons indices. We've got 2 electrons, so there's electron 1 and electron 2. Of course, we can't really label electrons, and even if we could, they're the same. So, that's the notation we're going to use. All right, now let's talk about the Pauli principle. The Pauli principle derives from quantum field theory, and the idea is that electrons are a kind of particle called fermions. And with that, I've already said everything I know about what a fermion is, other than that they have half integer spin. So there are some particles that have integral spin, like up, +1 or -1, but electrons aren't those. You've got either option of +1 or -1. And a consequence of the fact that they are fermions is that electrons in a molecule have to be indistinguishable. I mean, they can occupy different energy levels in a molecule, but in terms of the actual particle, the molecule can't change if you take this electron and call it number 1 and this electron and call it number 2 and then switch what you call them, right? It has to be exactly the same. And because each electron has to be indistinguishable, we're going to formulate the wave function of the molecule. And this is the jump, and it's kind of difficult. Formulate the wave function of the molecule such that each, and by wave function of the molecule, I mean the combination of all of the wave functions, all of the orbitals. So in our hydrogen example, this would be the bonding orbital and the anti-bonding orbital. We have to formulate the overall wave function of the molecule such that each electron contributes some to each orbital. That's kind of bizarre. What that means is in our molecule with 2 electrons with opposite spin, we can't say which electron is in phi 1 and which is in phi 1 with the bar. Both electrons contribute evenly to both of those orbitals. Yeah.
So if we look back to like something like sodium
Uh-huh.
that has like multiple orbitals,
Uh-huh.
that has, or I don't know, carbon that has S and P,
Right.
all of those electrons are really contributing to both S and to both P.
Right. So if you've got carbon, which has 6 electrons, the 1s, the 2s, and then 3 2p orbitals, we're never really going to say this electron here, electron 1, is in the 1s orbital, whereas electron 2 is in the 2s orbital, and so on.
So drawing like the little boxes is like basically irrelevant.
No, it's relevant in the sense that each wave function contains overall 1 electron's worth of charge. It's just that that electron is actually a linear combination of all the electrons in the molecule. And in terms of why it has to be that way, I don't know. I mean, that sort of derives from quantum theory. But it makes sense from the point of view that all electrons are identical and you can't tell one from the other.
Yeah.
So a consequence of this idea that they have to be indistinguishable is that, and why this is a consequence, again, comes from the theory. If you switch or permute the locations of 2 electrons, you get the opposite of the original molecular wave function. And this is called the antisymmetry requirement. So what do I mean by permute? I'm going to define P with a subscript I and J as a permutation or switcheroo operator that exchanges electrons I and J. We've got electron I is the label for that electron, and J is the label for the other electron. And I'm going to use the Greek letter psi to represent the wave function of the overall molecule. Oh man, my wrist is getting tired. I've been writing too much. So what this antisymmetry principle is that if you take electrons 1 and 2 in our 2-electron system and you switch their places, we're applying the permutation operator and we're switching, I don't want to waste time on that comma, we're switching electrons 1 and 2. Once you do that, you have to get the opposite of the wave function. Okay? All right. Questions so far? And again, it's okay if it's unclear why this has to be the case, because that's just derived from the theory, which I don't understand. Like, what are we paying you for then, right, is the question. All right, the original formulation for the wave function early on, developed by Hartree, said, okay, if I have 2 spatial orbitals, 2 electrons of opposite spin, I'm simply going to make my molecule by multiplying the 2 wave functions together. This represents the product of the wave function with spatial distribution 1 of the first electron, and then the same spatial distribution but opposite spin with the second electron. The problem with that is it doesn't obey the antisymmetry requirement. So if we permute electrons 1 and 2 in this Hartree formulation, we would get electron 2 in phi 1 and electron 1 in phi 1 bar. And that is not the opposite of our wave function. Doesn't obey the antisymmetry requirement. So one of the, and that was a decent approximation for the at the time, but we needed a better formulation for the wave function. So your text just comes up with this out of nowhere, and I'll try to explain a little bit about what it physically means. But the new formulation of the wave function is to say that The overall wave function for the molecule is electron 1 in phi 1 and electron 2 in phi 1 with the bar. And then we're going to subtract, oh dear, electron 2 in phi 1 times electron 1 in phi 1 bar. So we've got a regular term here and then a negative term where we've switched places for the electrons. Now, it just so happens, why would you do it this way? What does that mean? We'll talk about what it means in a physical sense, but why would you do it this way? Because if I permute electrons 1 and 2, switch their places, I come up with electron 2 in phi 1, electron 1 in phi 1 bar, electron 1 in phi 1, and electron 2 in phi 1 bar. Oh, hold on. Do you see that these two are opposites of each other? Yeah. So if we write our wave function this way, it will automatically obey the antisymmetry requirement. And that's going to make it so that our wave functions are physically realistic. Okay. Okay, questions so far? So sometimes rather than represent the wave function this way, you may have noticed, it's okay if you didn't, that actually this wave function has the form of a determinant. A determinant is a particular kind of product that you make from elements of a matrix, and you get it from linear algebra. So if you've never had linear algebra, my guess is you still had some algebra and did some determinants. You ever done a 2x2 determinant before? Maybe you've done a 3x3 by hand. Nobody does that anymore. You just ask the computer to do it. Nevertheless, if you write the wave function like this, that is equal to the way I've written it above. Because, of course, if you have a determinant like this, that equals A times D minus B times C, right? But there's also included in the front is a normalization factor that makes it so that the overall wave function, if you take the product of this wave function times itself, it equals 1. All right. Don't worry about this normalization factor. I've included it simply for convenience. All right, but look at the columns of this determinant. Notice that in this column I have phi 1, and I have electron 1 in phi 1, and then electron 2 in phi 1. So this column literally represents the fact that I can't say whether electron 1 or electron 2 is in phi 1. I know overall phi 1 contains the amount of charge for one electron, but I'm saying that electrons 1 and 2 contribute evenly to that orbital. Okay? Similarly with phi 1 with the bar. And so that's a total step to make one thing, so we're good to go. All right, so Samantha asked, what if you had more electrons than just 2? And the answer is you just continue on with the pattern. So imagine a 4-electron system in 2 spatial orbitals. So for that, the wave function would be, here's a scaling factor in the front, which you can ignore. We would simply do the 2 spatial orbitals in the first row with electron 1 in them. So this represents electron 1 contributing to phi 1 and its opposite spin partner, and then phi 2 and its opposite spin partner. And then we'll do the same down the table, only with electron 2 instead of electron 1. And then with electron 3. And this starts to get kind of tedious, and at this point you're seeing why we use computers. And there's actually a more efficient way of representing this determinant, but it gets challenging. It requires some linear algebra notation, and I didn't figure, I learned it in order to figure out that I understood this stuff enough to teach you about it, but I don't think it's worth learning. So we'll just write it like this, okay? We're not going to worry about expanding out this determinant, but this is another example of a Slater determinant which obeys the antisymmetry principle. The columns represent the fact that all 4 electrons contribute to phi 1. The rows represent the fact that 1 electron is actually spread apart in the 4 orbitals that we have. And as I said, this obeys the antisymmetry principle. Now, it's an interesting property of determinants that if any 2 columns are identical to each other, the determinant goes to 0. I'm not going to demonstrate that. Sure, why not? Let's do a 5 by 5 determinant. No, this is a determinant. The 2 columns are equal to each other. 2 times 2 minus 2 times 2 is equal to 0, right? That's true for any arbitrary any determinant of arbitrary size. So if, for example, column 2 were the same as column 1, that would basically be saying that 2 electrons occupy the same spatial orbital with the same spin, and then the wave function collapses. That is the more usual formulation of the Pauli principle. So the consequence that 2 electrons can't have the same spatial distribution and the same spin, that's a direct outcome of the antisymmetry requirement, which is kind of cool. So now you know a little bit about where that exclusion principle comes from. All right. Now we want to talk about applying this formulation for our wave function to the Hamiltonian. And remember that if we want to determine the energy of a particular orbital, we're going to want to know this quantity. And I've told you we've already included a normalization factor, so the square of this wave function is going to equal 1. So I'm just going to erase that because we're dividing by 1. If we want to know what the energy of this overall wave function is, we should apply the Hamiltonian to it, right? And just to remind you, that Hamiltonian is equal to, you've got the kinetic energy term, we've got the second derivative with respect to some coordinates for electron I. And let's say that we start with electron 1 and we go up through electron 2n. N here equals the number of spatial orbitals. So we have 2n electrons because each spatial orbital has 2 electrons. So that's the kinetic energy term. Then on top of that, we have, let's see, Q of a nucleus, Q of an electron, and then the sum of the distance between a nucleus and the electron I. And we're going to just sum that over all nuclei. So n equals 1, and we go to however many nuclei we have. I'm not going to put another letter there. Okay. That's the Coulombic attraction between the nucleus and electron. Now, we haven't yet included electron-electron repulsion, but what I want you to notice so far is that both of those terms are one electron operators. The second derivative operates only on electron I, right? And this Coulombic expression only cares about the positions of the nuclei and electron I. So we're going to summarize this in terms of a one electron operator. And we're going to call this the core integral, or the core operator. So H with the core on it. And we're going to put an I here to represent each electron from 1 to electron 2n. And this operator represents this function applied to just electron I. Okay? Now, the other part, of course, is repulsion between the two nuclei. And so this is going to be related to the charge of electron I and the charge of electron J, which are, of course, constant. And then we'll sum that with electron I and electron J equals I plus 1. This is just a way of saying we don't count. Don't worry about this notation. This is just a way of saying we don't count the same electron pair twice. But this integral, or this operator, is a 2-electron operator. It requires you to know the position of 2 electrons. That'll be important in just a little bit. Okay, so if you take this function, this wave function, and then apply the operator to it, you're going to get out a set of equations, a set of 2n different equations, where n is the number of spatial orbitals we have, 2n is the number of electrons. We apply this determinant, the operator, to this determinant. We're going to get 2n different equations, one for each wave function. So formulating the wave function as a Slater determinant is a way to take the overall wave function in the molecule and split it up into individual parts that we can deal with individually. And that's where the HartreeFock equation comes in. Now, I spent, like I said, most of yesterday trying to figure out where the heck that came from. And I sort of understand it. But because I only sort of understand it, not sure it's that useful for me to take you through it. If you're interested and want to see more, I'm happy to talk to you about it. You can come to my office. It'll probably require an hour and a half, and I will make lots of mistakes. And in the end, you'll understand it only probably worse than you did before. Or we can just trust that the people that did the math knew what they were doing. So, are you guys okay with that?
Yeah.
I'm the kind of person that likes to know things sort of like, if I feel sometimes if I haven't seen the derivation, I don't really understand what it means. And at some point, when there start being integral symbols and weird linear algebra things, you lose me. So we're going to apply the Slater determinant to our Hamiltonian, or apply the Hamiltonian to the Slater determinant. And what we're going to get out are these HartreeFock equations. So let me show you the HartreeFock equation. That's always fun to say, and you got to be a little bit careful with your vowels. And I'll explain what each term of this equation means. all multiplied by wave function I. And this could be for electron I or J. And that's going to equal some energy for that electron times the, again, wave function for that electron. Okay? The phi with the subscript I simply represents each one electron wave function from the Slater determinant. Phi 1 or phi 1 bar, phi 2 or phi 2 bar. I haven't figured out a way to put the bar or not on top of that, so we just won't. We'll pretend. Okay. E represents the energy of that particular one electron wave function. H double I derives from this core operator. In other words, if I take, say, for phi 1 with electron 1 in it, and I apply the Hamiltonian for that core Hamiltonian that contains kinetic energy and nuclear attraction for electron 1 to the phi 1 with electron 1 in it, this is the H11 integral. And that's a favorable number. That basically describes how favorable it is to have that one electron near that nucleus or that set of nuclei with the kinetic energy that it has. We call that a core integral because it only involves the single electron with its environment. Okay, questions about where that comes from? J and K derive from this 2 electron operator here. And to deal with this, we need to go back to thinking of the wave function in terms of a determinant. All right? So let's copy what we said here for our wave function for a molecule that only has 2 parts, 2 electrons, right? And for the sake of not having to write things again and again, let's just represent this as I1, J1, I1 J2 minus I2 J1. Is that okay? All right. So let's see what happens when we take this quantity and apply it to that 2 electron operator. Because the core integral is just the core Hamiltonian is just a 1 electron operator. Actually, the fact that it's a Slater determinant doesn't matter. Everything that's not the 1 electron gets eliminated from the expression. But because you've got a 2 electron operator here, you've got to consider the Slater determinant of the wave function. So to keep things simple, we're going to let the constants be implied. We're going to just represent this operator as 1 over r, the distance between the 2 electrons. So in this case, that's electrons 1 and 2. So applying this wave function, I1 times J2 minus I2 times J1, applying the wave function R, applying the operator R12 to this I1 J2 minus I2 J1, we can expand that out. Integrals, by the way, you can separate out as sums. So if we take this operator and apply it to this first term and then multiply it by the first term, we've got I1 J2 times I1 J2. And this is repulsion between electrons 1 and 2. which is easy and makes sense. And we're going to get another term out of that that's basically a similar quantity, I2 times J1. That's also Coulombic repulsion. And we're going to represent this as the letter J with a subscript I and J. So that's in our HartreeFock equation, that's where the J comes from. The 2 comes from the fact that you've got 2 different spatial orbitals here, and each can have 2 electrons. So there's actually 2 repulsion terms per spatial orbital. All right. And we'll have to leave off, dang it, we'll have to leave off the next term. What happens is when you apply this wave function, say, to this, this operator to this term, and then multiply it by this term, where there's a switch in where the electrons are. And that we'll have to deal with next time. So I'm sorry we didn't quite get there. It's okay if this is confusing. I'm not going to ask you to derive this from first principles, but I do want you to sort of understand the basic ideas. So we'll finish up with this next time, and we'll move on to chapter 1.